Good morning, good afternoon, good evening. This is Professor Atief Mohammed. Series of Lecture 7 DQ Networks or DQN. And let's get started as where we left off in Lecture 6. Today we are diving into one of the landmark algorithms in deep reinforcement learning, the DQN. This is about when DeepMind published the paper in 2013 and expanded it into 2015, genuinely surprised the research community by showing that a single algorithm could learn to play dozens of Atari games at a superhuman level using nothing but raw pixels at the score signal. By the end of this lecture, you'll understand why classical Q learning hits a wall on the real-world problems, how a neural network fixes that wall, and what two clever engineering tricks, experience, replay, and the target network make the whole thing stable enough to actually train. So let's get into it. So here's the roadmap for today. We'll open by diagnosing what breaks in standard tabular Q learning when state spaces get large. From there, we move to the core idea of neural Q approximation, replacing a look-up table with deep network will then drive the Bellman loss that we minimize to train that network. The second half of the lecture is about stabilization, why naively plugging a neural network into Q learning diverges, and how experience replay and the target network independently address those instabilities. We'll close by putting the full training pipeline together so you can see the algorithm as a whole. Each section builds on the last, so the order matters. So why Q learning breaks? Before we can appreciate DQN, we need to be honest about the limitations of what came before it. Tabular Q learning is an elegant algorithm with provable convergence guarantees, but those guarantees come with a silent asterisk. They assume you can store and visit every state action pair. The assumption collapses the moment your state space grows beyond few thousand entries. This discussion is essentially a motivation. We are going to look at two concrete failure modes, and memory problem, that generalization problem, and see exactly why they make tabular methods unusable for anything resembling a real environment. Understanding the failure sets up the solution perfectly. So let's be precise about when tabular Q learning works well. It shines in small, finite environments like grid world, simple mazes, or toy MDPs with a few hundred states. In those settings, you can literally write out the entire Q table, guarantee that every cell gets visited, and prove the values converge to their optima. The table is also completely interpretable. You can open it up and read exactly what the agent thinks about every situation. So this is a very decent thing that you must look into. Now flip to the right column. The moment your state space becomes large or continuous, think camera images, joint angles, or LiDAR readings, and table becomes physically impossible to store. Worse, even if you could store it, you would never visit most states during training, so most entries would remain at their random initialization. There's no generalization. The agent learns nothing about state A from its experience in nearby state B. That's fatal flaw for real robotics or game playing agents. Curse of dimensionality. It is a formal name for this exponential blow up. As you add input dimensions, the number of dentists, let's say if there are two dentists who are working in two different states, how they will look at your teeth issue. That's a real life example. However, the exponential blow up needs states that does not grow linearly. It grows multiplicatively. Each new dimension multiplies the state space by the number of values the dimension can take. A concrete example makes this visceral. An 84 by 84 grayscale Atari frame has over 7,000 pixels. Even if each pixel only took 256 values, the number of possible frames is 256 to the power of 7056. A number are so large it has no physical meaning. Real robots compound this further. A robot with 10 joints and 100 position bins per joint has 100 to the power of 10 states and partially observable environments. So when I said dentists, every dentist who's working on your teeth while opening your mouth up has partially observable environment. I want to bring that example back for you to reconsider that there are times when there are some areas of the teeth which a dentist is dealing with in terms of cleaning or in terms of preventing you for future teeth decay. They have to go through partially observable environments. So let's get back where the agents can't even see the full state. Things get even worse. No table-based method can touch problems at this scale. Function approximation, the insight that unlocks everything, is surprisingly clean. Instead of storing a separate Q value for every state action pair, we learn a function that takes a state and action as input and outputs, a Q value estimates. We write this as Q of SA semicolon theta, where theta are the parameters of that function. The critical advantage is generalization. If two states are similar, a well-designed function will map them to similar outputs, even if the agent has never visited one of them. We are no longer memorizing, we are learning structure. And the most powerful class of function approximators we have available, the ones that have proven themselves on images, speech, and language, are deep neural networks. That's the bridge from Q learning to DQN. The DQN architecture makes one elegant design choice. Instead of feeding in a state action pair and getting back a single Q value, we feed in just the state and get back one Q value for every possible action simultaneously. A single forward pass through the network gives us full functional action value vector. The greedy policy then just takes the argmax of that vector. Whichever action has the highest predicted Q value gets selected. This is an off-policy algorithm, which means the data we learn from does not have to come from the current policy. That is important because it lets us store and reuse past experience freely. Training itself is standard gradient descent. The computer loss backpropagate through the network and update theta. The same machinery that trains image classifiers now trains our reinforcement learning agent. That is the power of DQN framing. Now that we know we want to use neural network, we need to work out the details. What exactly does the network look like? What does it take as input? What does it take output? And how do we write down a loss function we can differentiate? This section answers all three questions. The Q functions or Q function Q of S A semicolon theta is parameterized by the weights and biases of a neural network. These parameters theta are shared across all states. There is no separate model per state. Instead, the network encodes everything it has learned about the environment into a single set of parameters that it applies everywhere. From an architectural standpoint, the network's hidden layers do the heavy lifting of representation learning. For image-based environments, we typically use convolutional layers to extract spatial features, edges, objects, motion, patterns, before passing those features into fully connected layers that produce the final Q value estimates. The output layer has exactly as many neurons as there are actions. Higher output values mean the network believes that action leads to more cumulative reward from this state. The key thing is to internalize here that the DQN is, as its core, a supervised learning problem in disguise. We are trying to get a neural network that to match a set of targets. The twist, and it's an important one, is that those targets are themselves computed using the network we are training, which introduces instabilities that don't exist in ordinary supervised learning. We'll name that problem here and solve it in this section. All right, let's move to network I/O. Let's be specific about what does in and what comes out. On the input side, Atari DQN stacks four conservative frames to give the network a sense of motion and velocity. A single frame tells you where objects are but not which direction they are moving. Those staked frames are pre-processed to 84 by 84 grayscale and normalized for continuous control tasks. The input is instead a feature vector of joint positions, velocities, and sensor readings. On the output side, we get one scalar per action. For Atari breakout, that's four values: do nothing, fire, left, right. For more complex games, it could be 18. The key insight is that we evaluate all actions in a single forward pass, which is computationally far more efficient than running the network once per action. At interference time, we take the argmax over outputs. If we want a stochastic policy, we can apply softmax instead. The Bellman equation is the theoretical bedrock of Q learning. It tells us that the optimal Q value for the state action pair should be it is the immediate reward you get plus the discounted value of the best action you can take from next state. We write the target as y equals r plus gamma times the max over a prime of q of s prime a prime semicolon theta minus. So the loss function follows directly from the Bellman target. We want our network's prediction q of s a theta to match the target y as closely as possible. So we minimize the expected square difference between them. This is the mean squared Bellman error, and it is the objective we pass to our optimizer. The expectation is approximated to practice the sampling a mini batch of transitions from the replay buffer, typically 32 or 64 examples. For each sample transition, we compute y using the target network and the observed reward, compute the prediction using the online network. Take their difference, square it, and average over the batch. Crucially, gradients flow only through q of s a theta on prediction side. The target y is a constant in this computation, so we stop gradients there. This is what makes it semi-gradient method. Let's make sure that the intuition is solid before we move on. At every gradient step, we have two quantities, what the network currently predicts for q of SA and what we want it to predict, the target y derived from the Bellman equation. We are pulling the prediction toward the target by taking a small gradient step. Think of y as a teacher's answer and q as the student's current guess. Each update nudges the student a little closer to the teacher. Why generalization matter? One of the most powerful things a neural network brings to reinforcement learning is the ability to generalize to produce sensible Q value estimates for states the agent has never explicitly visited. In a tabular agent, if you have never been to state S, your Q value is just whatever you initialized it to, typically 0. In a neural agent, the network extrapolates from nearby states it has been. This comes from shared feature representations. When the convolution layers learn to detect a ball moving toward a paddle in breakout, what representation is useful across hundreds of visually similar frames, the agent does not need to visit every frame independently. This is why DQN can achieve superhuman performance after seeing only fraction of the possible game states. That said, generalization is not magic. Spurious correlations happen, and the network can make confident but wrong predictions in states that look superficially similar to one it knows. Keeping that caveat in mind is important when debugging reinforcement learning agents. Stabilizing DQN is our next discussion. Let's jump right into it. So we have now established the architecture and the loss function. Theoretically, we should be able to run gradient descent and get trained agent. In practice, doing exactly that, plugging a neural network naively into Q learning almost always diverges. The research community spent years before DQN struggles with this, and the original DQN paper, the real contribution was identifying and solving two root causes of instability. Experience replay is the first stabilization technique. The idea is simple. Instead of training on transitions as they arrive from the environment, we store every transition, the tuple of state, action, reward, and next state, in a large circular buffer called replay buffer. When it's time to take gradient step, we sample a random mini batch of that buffer, then using the most recent experience. Why replay works. The core problem with learning from consecutive transitions in correlation, if you are playing Pong and the ball is moving left, and the next 100 frames are all going to look very similar, and the agent is going to take very similar actions. So training neural network on 100 nearly identical examples back to back causes it to overfit catastrophically to that narrow slice of experience while forgetting everything else it learned. This is called catastrophic forgetting, and it is known failure mode of neural networks on non-stationary data streams. The target network is the second stabilization technique, and it addresses a different problem. Recall that our Bellman target y depends on q of s prime a prime semicolon theta. The same theta we are updating without any intervention. Every gradient step changes theta, which immediately changes all future targets. It is as if every time you take a step toward a goal, someone moves the goal. Why target networks work? Mathematically, so if I use the notion, the mathematical reason or mathematical reasoning, the target network helps is that it converts a moving target optimization problem into a sequence of fixed target problems. Within each freeze window of C steps, y is the constant with respect to theta. That means the loss landscape is stationary during that window, and gradient descent can make consistent progress toward a well-defined premium. The final piece of DQN training loop is exploration strategy. The agent faces a classic dilemma. To learn good Q values, it needs diverse experience, but its own greedy policy will only visit states it already thinks are valuable, missing large parts of the state space entirely. Epsilon greedy is the standard solution with probability epsilon can ignore. And technically, with the probability epsilon, we ignore the Q values and take a completely random action. Otherwise, we take greedy action argmax Q of S and A. So let's consolidate everything. DQN is fundamentally Q learning with a neural network as the function approximator. That single change replacing a table with a network makes the algorithm applicable to raw images, image inputs, and high dimensional state space that would be completely interactable for tabular methods. The training objective is the mean squared Bellman error derived directly from Bellman optimality equation and minimized with standard gradient descent. Happy learning. See you in the next lecture.